space. H is, so what I'm going to do is I'm going to say space is 0, A is 1, B is 2, and so on. Then this string is represented by 8, 5, 12, 12, 15, then the space, which is 0, and so on. And then I can represent each of these characters by three ary symbols. So 8 would be 0, 2, 2, 5 is 0, 1, 2, 12 is 1, 0, excuse me, 1, 1, 0, and so on. So usually, in fact, almost always we'll be talking about powers of 2, but nothing really changes too much if we're talking about primes, powers of 3, powers of primes. Everything is the same. Doesn't really matter too much what m is. Just to make the following comment. So we're usually going to compare systems in terms of bits. Bits are the fundamental unit of information. So if I tell you, usually if I want to tell you how much information I have, I describe that in terms of bits, or something that's easily translatable into bits, like bytes. So what we're going to want to do is we want to compare systems fairly. So we're generally going to want to reduce any information units down to bits. So we're going to talk about symbols and bits. So a symbol is one of the M-ary characters that you're allowed to send. In other words, 0, 1, and so on, up to m-1. Whereas bits just gives you a way to measure the amount of information that you're sending. So how many, if I have M-ary, an M-ary communication scheme, then how many bits do I have per symbol? So in other words, okay, let's think of some examples. 4-ary, how many bits per symbol? 2. Why is that?
1, 1, you can.
That's right, so in 2 bits I can express 4 levels, so that's 2 to the 2 equals 4. 8-ary, 3, because 2 to the 3rd power is 8, so I have 3-bit positions, each one of them has 2 possibilities. So therefore 8-ary I can express 3 bits. How about 3-ary? Now the translation's not obvious, but what did I do here? What did I do to get 2? I took the exponent of 2 to the power, and basically whatever that power was, that's how many bits per symbol. So how do I knock out that power?
Log.
Take the log. Take the log base 2. Take the log base 2. So 3-ary, I would have log base 2 of 3. And that would be 1.585. So at this point, we're kind of talking about the average number of bits per symbol. Obviously, we can't design a system assigning exactly per symbol by symbol, assigning 1.585 bits per symbol. That's just ridiculous. But it is possible to design asymptotically long schemes in which you can attach, on average, 1.585 bits per symbol. So what we're going to do is we're going to do things like, I mean, it's obvious how to calculate quantities like energy per symbol just by taking my set of modulation functions, calculating the energy in each one, taking the average. But what I really want to do is I want to take, I want to compare systems fairly, so I want to compare them in terms of, information sent. The fundamental unit of information is the bit, so I want to translate symbols to bits. So in other words, if I have energy per symbol, I then multiply by bits per symbol to get the energy I use per bit. So that's how I compare systems fairly. And any other scheme. Actually, this would work in your favor for bit rate. So generally, in most systems, the symbol rate is the same. So the symbol rate is constant. The maximum number of symbols you can send per second is the same. So if you want your bit rate, in other words, bits per second, you multiply by bits per symbol. Okay, let's tie this back to signal space. Actually, let's do a quick example. Let's say my system allows me to transmit 1 times 10 to the 6th symbols per second. What is the bit rate in binary, 3-ary, and 4-ary? So the bit rate is bits per second. So therefore I need to multiply this by bits per symbol. So in binary, how many bits per symbol? I have symbols 0 and 1, 2 possible symbols. How many bits per symbol?
1.
Just 1. So everything we've been looking at up until now has been binary. And in binary, there's only 2 possible symbols, and so every time I send a symbol, I'm just sending a bit. So therefore the bit rate is the symbol rate times 1, which is 1 times 10 to the 6th bits per second. In 3-ary, we just had that the bits per symbol was roughly 1.585, so that's 1.585 10 to the 6th bits per second. And in 4-ary,
2.
it's 2.
2.
So if you can expend the energy to go from binary to 4-ary, you can double your bit rate even though the symbol rate stays the same. Okay, tie it back to signal space. Initially, the tying back is going to be trivial. So let's talk about one-dimensional signal space, which is exactly what we've been talking about so far. So in a one-dimensional signal space, like a one-dimensional vector space, there is only one basis vector. So let's call that S of k, which is defined on